real number coefficients. If you're coming up with coefficients that have I in them, either you're forgetting about the fact that the complex zeros come in pairs, or there's some kind of issue with your multiplication, right? So look at your last polynomial. If your final polynomial has I as a coefficient, then you have some kind of problem there. So we're going to write the polynomial with the real coefficients and the given zeros. We know if negative 1 minus 3i is a 0, then its conjugate is also 0, which would be negative 1 plus 3i. So I'm going to start writing my polynomial, and because I only have two zeros and they're imaginary, I can think about this function. This must be what type of function? What's that?
Quadratic.
It must be quadratic, so it only has two solutions. And, you know, like think about a quadratic that would have two imaginary solutions. It could be a parabola that opens up and is above the x-axis, or it could be a parabola that opens down and is below the x-axis. So we're going to write a polynomial that has these zeros. So I'm going to set up my factors x minus k. Now I'm going to do this differently because we did it on Friday, so now I'm going to take a little shortcut here. I'm going to write x minus k, but I'm going to go ahead and distribute my negative to both parts of the complex zero. So I'm going to do x minus negative 1 and also minus negative 3i. So are you okay with me writing like this? X plus 1 plus 3i is my first factor. I've distributed the negative to all parts of that first complex zero. So the negative 1 and the minus 3i both became positive. Okay. And then I'm going to take another little shortcut here. I'm going to do x minus k for my next zero. So I'm going to do x minus negative 1 and also minus a positive 3i. So that's going to turn negative. Would you agree that we should have a factor that looks like x plus 1 minus 3i then? Okay, so for some people, you know, like in my notes I showed where I put those things in parentheses and then I distributed. Some of us may be able to jump over that step and we'll just go ahead and distribute the negative. Just be real careful here. The first two terms should always look exactly alike, so they both look like x plus 1 in both factors. Never should you have like complex conjugates that you put back as factors, and one is x plus 1 and the other is x minus 1. They'll always look exactly like, oh, she's in here. Sorry. Okay, so now I'm going to show my shortcut version, which is what most mathematicians will use. So like I taught you to just go ahead and FOIL that out, like trinomial by trinomial to get 9 terms and the i's will cancel. That's totally fine if you want to continue doing that. I'm going to show that other method where you regroup the two terms in the front that look exactly alike. So do you agree x plus 1 is the same in both? Okay. So mathematicians are going to group the x plus 1's together, and they're going to say, that whole x plus 1 in parentheses, that's going to be like my a, my first term. And then I have plus 3i, which is like my plus bi. And then in the other one, I have that same a again, x plus 1, and now I have minus bi. So I have a set of complex conjugates. That day we did complex number operations, I went ahead and multiplied that out one time. Does anybody remember what complex conjugates always multiply to be? A squared plus b squared. So they'll always multiply to be a squared plus b squared. Here's the shortcut. If you are okay with this regrouping and seeing those as conjugates, then you can take your a, which is x plus 1, square it, and add to it b squared. B is just the coefficient to the I. So I could use 3, I could also use negative 3, but I'm going to square it so it's going to come out to be positive. So I usually always just pick the positive one. And then you just have to be careful with this. This is not x squared plus 1. It has a middle term. If I FOIL out x plus 1 times x plus 1, I'll get x squared plus 2x plus 1. I know that pattern very well, so I can do that lickety-split in my head. And then I get a plus 9. Did you guys get f of x equals x squared plus 2x plus 10 is your answer? Now, if that's something you're interested in, you like that conjugate rule that a plus bi times a minus bi always equals a squared plus b squared, you can use it. Note that the rule for complex conjugates is different than the rule of like a plus b times a minus b. When they don't have i's in them, it's always a squared minus b squared because the I squared doesn't take the second sign change. Okay, so just an FYI. If you did trinomial by trinomial and you still didn't get x squared plus 2x plus 10, let me know. I'll come around and look at your work. You must have some kind of multiplication, sign error, combining like terms error. Okay, we're going to do notes today here at the beginning. Did you guys need me to read the answers to 45 and 47, or did you check your answers in the back? Read it? Or no? I'm sorry, I can't hear you. I'll just read them. 45. Gotta find out where it was. 45 was x cubed minus x squared plus 25x minus 25. And 47 was x cubed minus 12x squared plus 46x minus 52. Okay, so today we're gonna reverse what we did on Friday. So on Friday, I gave you the zeros and you wrote the polynomials, like the warm-up. Today we're gonna focus on, can you find all the zeros of some polynomial? Now, this first example that we're going to do is really like a nice bridge between Friday and today. It's a little bit different than probably the majority of what you're going to see on your homework and what you're going to be practicing tomorrow. Note that tomorrow, if you check your gold sheet, we have a work day. You're going to have a worksheet. You'll be graphing lots of polynomials, doing different things for them. It'll be a really nice day for you to kind of like put all the things we've been learning in chapter 2 together and ask questions. So if you've been feeling like, I'm feeling a little underwater in chapter 2, tomorrow is a good day to kind of get yourself caught back up. Okay, in this example is a little bit different than what we're going to see later in our notes because it says use the given zero. So if I give you a 0, I would call that's a hint. If you think back to the quiz that you guys took on Friday, the very first polynomial, you had to do a whole bunch of stuff with it and then graph it. But step A said like verify a factor, and I told you what factor to verify. So to me, that's a hint. Like here, start division with this. Okay. So anytime I give you a hint, I would say a lot of times I'm going to think about using division because I know if that's supposed to be a 0 or that's supposed to be a factor, that if I do polynomial division, I should end up with 0 remainder. So it's kind of like a hint of where to go, what to start with. Now this one's a little bit different because look at my polynomial, it's cubic. And then look at my 0, it's imaginary. We've never really done synthetic with imaginary zeros. I would not recommend it. And I wouldn't really either recommend long division with imaginary zeros. You could see where this could get really messy. So we're going to basically use what we did in our warm-up. If -1 minus 3i is a 0, then -1 plus 3i is also a 0. So we found 2 zeros. How many zeros should we have total for a cubic polynomial? 3. And I gave you that warm-up on purpose. We already wrote the polynomial, right? Right, the polynomial for this. So these two are going to turn out, Zach told us it was going to be quadratic, and was it x squared plus 2x plus 10? Okay, so we already have that work from the warm-up. So now, if we know that those two zeros make this quadratic, and we have a cubic polynomial, we can use division, take our cubic divided by the quadratic, and we'll get left over with a linear factor. That's the missing factor, and we'll find our zero. So if you've been, having some difficulty with long division, we're going to do long division right now. Set up your long division. I really can't do synthetic with a quadratic, and I don't want to do synthetic with the imaginary zero, so I'm going to do long division. Put x squared plus 2x plus 10 in my divisor spot, and x cubed plus 4x squared plus 14x plus 20 in my dividend. Now, quick side note, if I ever do long division and there's like a term missing in the polynomial, I do always include a zero term for that, because I always like to keep, when I'm doing division, all my x cubes in a column, x squareds in a column. It keeps me organized. Okay, now, those of us who need to brush up on long division, only divide the first two terms. So the first term of your dividend, x cubed, divided by the first term of your divisor, x squared. Left over is x. So find the x term, put x above it in your quotient spot, and now we're going to distribute the x to all three terms of the divisor, okay, and then line them up under their like terms. So this is going to be x cubed plus 2x squared plus 10x. This is the part you just have to be really careful of. It's easy to make a small mistake here, and some of you, when you get your quizzes back at the end of class, you might have made this error where you didn't subtract everything. Okay. To avoid forgetting to subtract, I just go through this line and I change all the signs. So these are all positive, negative, negative, negative. And then I don't have to worry about forgetting to subtract. Okay, so I get what? 2x squared plus 4x. And then at this point, you probably want to bring down the next term because you'll want a trinomial. Your divisor is a trinomial. Okay. Now, restart division, but you can only divide the first terms at a time. So, first term down here is 2x squared. We're going to divide it by x squared. What's left over? 2. Line it up with the numbers. This is also how you know you're done dividing, because you've hit the end of the quotient. Everything else would be a remainder. We should get a remainder of 0 if we did that factor correctly. So now I'm going to distribute the 2 to everything. That would be 2x squared plus 4x plus 20. Since I'm subtracting the exact same thing. Negative, negative, negative. I get my 0 remainder, so it worked out. Okay. So this quotient right here, x plus 2, is the third factor. Okay. The first two factors were the ones we did in the warm-up. Okay. The third linear factor. And what is your 0?
-2.
X equals -2. So if you were listing out all the zeros, you could list -1 plus or minus 3i, and then also -2. Now you have 3 zeros for a cubic polynomial. That might be something else you'll need to look at when you get your quiz back today. Like I think 1B maybe asked you to write the complete factorization, and people were putting zeros right there. Or when it asked for zeros, you were writing factors. So the factors are the things that have plus or minus, like x plus 2. And the 0 is when you said equal to 0 and solve. Okay? So remember, use polynomial division like this if you're given a hint. And if I give you a hint that isn't imaginary, like I told you, find all the other zeros. If you know one of the zeros is x equals 3, then you could use synthetic. And then maybe work with your quotient after that. Okay, so we're going to move on. What if I don't give you a hint? What if you don't have a 0 to start with? How will you start finding zeros? That's called, yes, we're going to do synthetic guess and check, but we don't want to just guess random infinitely many numbers. We're going to create a list of possible zeros through, pre-calculus calls it the rational zero test. Algebra 2, we call it rational root theorem. They are the same thing. Think about like reading like a mathematician, that very first line, if the polynomial has integer coefficients, that's when you're allowed to use the rational zero test. So integers are what I call nice numbers, not decimals, not fractions, no radicals. If you have those integer coefficients, then every rational zero of the function has to be of this form, P over Q. And in Algebra 2, we probably wrote plus or minus P over Q, like the sign doesn't matter. Okay. Where P is a factor of your constant term, so that's at the back of your polynomial, and Q is a factor of your leading coefficient at the front of your polynomial. So I call those the bookends of your polynomial. Look at the two integers right there, find all their factors, and then you take all the factors of P and put them over Q's in front. You just make this long list. Is this vaguely familiar to us? P's over Q? Okay. Now, one thing to note is it's called the rational root theorem or the rational zero test. So this only helps us like write a list of rational zeros. Okay. There's no imaginary zeros here. There's no irrational zeros here. Your polynomial could have those kinds of zeros. Like you could have imaginary zeros, you could have irrational zeros, but we can at least make this small list of rational zeros to guess and check like Katie said. And then when we start guessing and checking, then we can start using our results to maybe factor, quadratic formula, find those other kinds of zeros. Okay, so we'll do an example here in just a minute, but we want to talk about one other helpful tool besides the rational zero test. It's called Descartes' rule of signs. So I know in Algebra 2, in Honors Algebra 2, we briefly cover Descartes' rule of signs. We don't stress a whole lot with it. I'm not sure about regular Algebra 2, so that might be something you'll have to read up more if we're unclear. And then Algebra 3, I think you probably have spent quite a bit of time with Descartes. Again, think about that first line. That first line in mathematician speak is just telling us when we can use Descartes' rule of signs. So f of x has to be a polynomial. It has to have real coefficients. And then your constant term should not be equal to 0. And then there's two checks for Descartes' rule of signs. One's for positive zeros and one's for negative zeros. They both involve counting sign changes. So that means like you're looking at the polynomial and you're going from term to term to see if it's going like positive to negative or negative to positive. So you're just counting how many times it switches over like that. Now I'm going to add a little piece right here. Okay, this second statement is, okay, obviously you're going to count the sign changes, but there's like just this one other piece that you have to consider. The number of positive or negative real zeros is going to be equal to the number of sign changes that you counted, or it's going to be less than that number by an even number. And that's because if some of your zeros aren't real, they're imaginary. We wouldn't really count those as positive or negatives. And those imaginaries are always going to come in pairs. So then that takes away 2 positive or 2 negative zeros each time. So if you have 0 sign changes, you have 0 real, positive or negative zeros, whichever one you're counting. You're done. If you have 1 sign change, you have 1 positive or negative real zero, and you're done because you can't go less than 1 by an even number. If you count 2 sign changes, then when you tell us how many possible zeros there are, or like possible positive or negative real zeros, if it was 2, you would say 2 or 0. So like maybe there's 2 positive real zeros, but maybe the zeros are actually imaginary and there's only 0. If you get 3 sign changes, then you would say 3 or 1. And as you keep going up, you have to keep going down the list. So like 4 would be 4 or 2 or 0. Because you could say like that there would be 4 imaginary zeros as well, so then you wouldn't have any positives. So always remember that you got to count down by 2s. Okay? Okay, let's look at this example just real quick to practice Descartes' rule of signs. X to the 4th plus x cubed plus 3x squared plus 1. Okay, for the positive real zeros, count the sign changes in the original function f of x. Do any of my terms change signs? Nope. So there are 0 positive real zeros. Meaning, if I go back to my list of plus or minus p over q's, if there's no positive real zeros, I'm not going to waste my time checking any positives. That would be pointless. I know they don't exist. So then I'm going to do the negatives on my list. Okay. Let's do the negative check. So for the negative check, you have to write out what f of negative x is so that you can count the sign changes. So I'll show my work for f of negative x. I'm plugging negative x in for all the x's. This is kind of like our even odd checks from chapter 1. So if I put negative x in for all the x's, remember the term will only change sign if it had an odd exponent. Because like negative x to the 4th with an even exponent is going to come out to be positive x to the 4th. So that didn't change signs. Negative x cubed, that'll be a negative, so it'll change signs. It's now negative x cubed. This one will stay positive because negative x squared is positive x squared, so it's going to be plus 3x squared. And then plus 1 doesn't have an x, so that's not going to change signs either. It has an even exponent of 0 on it. Okay, so now let's count our sign changes for f of negative x. We go from positive to negative, and then negative to positive, so we have 2. So we say 2 or 0. Negative, real, zeros. Because of the stuff I wrote in green. The rule for Descartes is the number of positive or negative real zeros is equal to the number of sign changes, that's our 2, or less than that number by an even number. Because maybe there are 2 negative real zeros, but it's also positive that there are none, and there's just another pair of imaginaries. What's the degree of that polynomial? 4. So there has to be how many zeros? 4 equal to the degree. Number of terms would be 1 less than the degree, but there have to be 4 zeros. So notice in Descartes' rule of signs, we've only accounted for 2 of them, which means 2 of them have to be imaginary, okay, if they're not real. So we know there's definitely 2 imaginary. There's either 2 imaginary, 2 positive, or 4 imaginary. Okay, that's what's possible. Okay, so Descartes' rule of signs. We're going to use it to narrow down our list. If we are making the list of plus or minus p over q's, don't check any positives because they're not going to work. Check the negatives and try to find a 0. Okay, let's do one example together. So I've got 2 parts to this, like what I want you to do for your answer here. We're going to write f of x as a product of linear factors. So that would be also like on the quiz when it asks for the complete factorization. So you have all the factors. And I also want you to list all the zeros. You know, on a problem like this, I probably am going to start with finding all the zeros. And then once I have the zeros, I can easily stick them back as x minus k factors. So we've got f of x equals 2x to the 4th plus 3x cubed minus 8x squared plus 3x. What do you notice about all those terms in that polynomial? They all have x. So I would actually start this one by factoring out the common term, x. You know, go back to Descartes' rule of signs. You can't use Descartes' rule of signs unless the constant is equal to not 0. So our constant is plus 0 back here. Let's factor out the x right away. So we could also say f of x in partial factored form is 2x times 2x cubed plus 3x squared minus 8x plus 3. Which, that means that this was a factor of x. So we know we have a 0 where x equals 0. So we know one of our zeros. We still have to find the other 3. Okay. Now, here's that polynomial, the cubic polynomial. I have it up here on the sideboard. Let me show you. This is also good for people getting their quizzes back. Some people attempted a factor by grouping. So I want to make this very clear. You might factor out the x squared from the first 2 terms, and you're left with 2x plus 3. And then I do need to take out a negative, but 8 and 3 don't share anything in common, so I'll just take out a negative 1. And then I'll have 8x minus 3. Some people told me then that my factors would be 2x plus 3, 8x minus 3, and the 2 factors, x squared minus 1, and maybe I would factor that again with difference of perfect squares, right? But that's not how factor by grouping works, right? If these don't match, 2x plus 3 and 8x minus 3 don't match, don't factor. The only time factor by grouping works is when they're the same. Okay? In fact, look at this. You actually have 4 factors here, which would mean that you had a quartic polynomial, but it was only cubic. So it doesn't even make sense. Like you've added a factor that shouldn't be there. Okay. So I can't factor it to solve. I'm going to use rational zero test. Okay, let's do our rational zero test. So this is going to be my possible zeros that I could check. Okay, go to your constant term 3. What are factors of 3? 1 and 3. Those are going to be your p's. Go to your leading coefficient. 2. What are factors of 2? 1 and 2. Those are my q's. Now I'm going to make a list of plus or minus all the p's over q's. So I'm going to take 1 and 3 and put them over 1. Well, that's easy, right? Plus or minus 1, plus or minus 3. Then I take all the factors of p, 1 and 3, and I put them over 2. If they produce a new factor that's not already on the list, then I should add it to the list. So like 1 over 2 is new, and so is 3 over 2. How many zeros are on my list? 8. 4 positive and 4 negative. We can use Descartes' rule of signs to maybe try to narrow down that list, so it's worth a while to check. I will have questions on quiz or test where we have to use Descartes' rule of signs, so I'll practice it here. So we're going to do the positive real zeros first. Okay, for positive real zeros, count the number of sign changes in the original polynomial. And we have already accounted for this factor of x, so we're looking at this cubic polynomial right here. Okay, 2x cubed is positive, 3x squared is positive, and then we switch to a negative. So we have 1 and 2. So we'll say there are 2 or 0 positive real zeros. For the negative real zeros, we have to look at f of negative x. Now, from chapter 1, you could probably do this without making the substitution. Like, you know which ones are going to change signs, right? The ones with what kind of exponents? Odd exponents. So this one's going to be negative 2x cubed. But this has an even exponent, so it's going to stay positive. This one has exponent of 1, so it's going to change. It's going to be plus 8x. And then this one doesn't have an x, so it's not going to change. How many sign changes there? Yep. We're looking at the x cubed one. Just remember to use Descartes' rule of signs in the rational zero test. Your constant can't be equal to 0. That would be really boring. Then your p over q's would all be 0. Unhelpful. Okay, so you got to factor that out first. We have one sign change. Okay, so what kind of information do I have from Descartes' rule of signs? Well, I could have, in this cubic polynomial, I could have 2 real and 1 negative. That would account for my 3 zeros. Or I could have 0 positive, 1 negative, and then the other 2 I might have to find through like quadratic formula or something like that. They might be imaginary. Okay. You go through with your group and go ahead and start checking some from the list. So we're going to do a synthetic guess and check like Katie mentioned earlier. We're just guessing and checking them. And like Brody clarified, do it with the one that's factored out, right? The cubic polynomial. We've already worked with this x. So 2, 3, negative 8, 3. I'm going to come around and spot on your paper, see if you find me a 0. I like your distribution of work. You add down first, so you have to drop your leading coefficient. 2, and then multiply. zero. So it's definitely not going to work. Kaylee found one. One works.
I think positive 1/2 works.
So I'm going to check 1, add down to get 2, multiply, we get 5. When we add, multiply to get 5, negative 3. Oh, sure enough. So I can add that to my list of zeros up here, right? X equals 1. Okay. Did anybody find another one that worked? 3 or negative 3? Negative 3. Okay. So one option you have, like if you're positive, so we just found a positive one, then we know there's another positive and there's a negative somewhere in there. So you might keep checking. So you checked negative 3 works. So I'm going to show my work. Oh yeah, it does work. Okay, so I can add that to the list. Actually, I'm just going to list these. So I have 0 from our first factor, 1, negative 3. Okay. Now, you could keep checking if you wanted to try to find like that last 0. What did you say you thought 1/2 worked? Positive 1/2 works. So you could keep checking in 1/2 and it should work as well. But what I do is I like pay attention. This was a cubic, right? 2x cubed. So when I divide once, then I'm at 2x squared. And if I divide again, now I'm at 2x and a number. So like this just transforms. This is 2x minus 1, isn't it? Set it equal to 0, and I would get x equals 1/2. So I like to use that. You could also have done that right here. So like this one was 2x squared in the middle. So this is 2x squared plus 5x minus 3. I usually stop at quadratics and write it out because either I can factor it or like what if the other two are imaginary or something like that, then I might have to quadratic formula. So I might have done all these checks and I was never going to find anything. So I usually like to go here. This one does factor. It would be 2x and x. And then I just have to figure out I need my last terms to multiply to 3, and one is positive, one is negative, because it's a negative 3. But I need my middle terms to add to 5. So think about how you could multiply by 2 and 1. Well, I want to get a 6x on the outside, have it be positive, and then I want to have a minus 1x on the inside so that I get plus 5x. And then I'll have a negative 3 in the back, which there's my factor of 1/2, and there's my factor that produces x equals negative 3. So I like to factor out a quadratic, but if you keep guessing and checking you're not wrong, just be aware that if the answer is like imaginary, you're never going to find it. So you might have to write out the quadratic and quadratic formula or something like that. Okay, how many zeros do we have up here? We have 4 zeros. What's the degree of our original polynomial? 4. So we know we have all the zeros. Okay. Remember, it wants us to also write out the product of linear factors. Okay. So I would say f of x equals, of course, the x we factored out in the beginning. The first 2 zeros are easy ones to write. X minus 1 and x plus 3. The one you have to be careful of is if you found the 0 1/2. You don't want to write x minus 1/2 because then your first term would just be x to the 4th. And look, it's really got a 2 in the front. So how else could you get a 0 of 1/2 if it were 2x minus 1 like we had found? So sometimes you have to tweak that one that looks like a fraction and put the coefficient back on the x.
0 counts as positive.
No, 0 is not positive or negative. So you only have 2 positive zeros, 1 and 1/2, and you have the 1 negative. Yeah. Okay. So does that sort of seem familiar from Algebra 2? I did do this one with the factor of x because that seems to trip people up here, but you just need to move it out and then continue on your normal path. Okay, we've got about 5 minutes. If you have been having issues with the online textbook and you want to like pull out that textbook from your pods and take pictures of your assignment, you can do that. I'm